Okay, welcome to Level 1 Science Online with Henny van Vieren.
Okay, hello Year 11s, welcome back to another lesson. Today we're going to be talking about mass specifically and other forces, just continuing this discussion around forces and motion. Okay, so without further ado, on with the lesson. Okay, so a force, a mass, and an acceleration. The force experienced by an object can be calculated by multiplying the mass of the object by its acceleration. Okay, so have you guys seen the videos of the cruise ship that crashes into, um, what do you call it, into the harbor bridge or whatever? Not the bridge, but the mooring place. It is a humongous piece of machinery. So the mass is huge, but the force or the velocity and the acceleration is really slow, but it still has a humongous force. For instance, a bullet, when you fire a bullet, it's got a small mass, but the acceleration is so enormous that it has a big force. If you take a small stone with a small mass and you throw it slowly at somebody, the impact will be relatively low. Very little force is going to be felt. Take that small stone, put it into a slingshot, and then shoot it at something, and you can break glass. You can even, don't do this, but you can even kill small animals. So, yeah, and please don't shoot each other with slingshots. You only get one set of eyes, you don't want to lose them. Anyways, but if more force is applied to an object, then it will accelerate faster. So if this goes up, this will also goes up. Now remember, we can put that into our triangle. Mass and acceleration is going to be at the bottom and force is going to be at the top. Okay, and this is actually Newton's second law. So the force of something is directly equivalent to the bigger the mass, the bigger the force. The bigger the acceleration, the bigger the force. Okay.
May the force be with you.
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 May the force be with you, Master.
May the force be with you.
May the force be with you.
May the force be with us.
May the force be with us all.
May the force be with you. Interesting that today is the 1st of May, and remember, Monday is Star Wars Day. May the 4th. Okay? Anyways, so Newton's second law said, when forces are not balanced, the second law states that the acceleration of an object is dependent upon two variables: the net force acting upon the object and the mass of the object. Okay? The acceleration of an object is dependent on two variables, the net force and the mass. So it comes into this: force equals mass times acceleration. So if you have a trolley that's empty and you push it with a certain amount of force, your acceleration is going to be big. But if you push a trolley full of stuff with the same force, you will have a much lower acceleration. If you push that same massive trolley, but you're using a much bigger force, you will have to put in a lot more force to get the same acceleration as you did over here for the trolley that was empty. Okay, so these play into each other all the time. F equals ma. So here's Ben. Ben is amazing. He can push both a car and a lawnmower, so they accelerate at 0.5 or half a meter per second. The mass of the car is 950 kilograms, and the mass of the mower is 10 kilograms. What is the force required to accelerate the car compared to the lawn mower? Okay, so let's think about this. We have, what is that? We have the acceleration, don't we? Yep, so we have we have the mass for the car. Yep, so we can do m times a gives us the force. And we have the mass of the lawnmower, and we have the acceleration. Now guys, just remember, when you see kilogram and gram, that is your mass. Okay, that is how massive you are. That is the number of molecules that you consist of. It never changes. You don't suddenly go to the moon and become smaller. You're still the same massiveness, but your weight force, that is the force, and we'll get to that later, but your weight force changes. But just remember for now, kilograms and grams is mass. So if we take 0.5 for the car and we multiply it by 950, so half times 950 gives us 475, and force is measured in Newton. If we take 0.5 and multiply it by 10, that's half times 10 gives us a 5 Newton. So you can see that it is very different, but because the mass is different. Okay, so the car is 950 times a half is 475. Lawnmower is 10 times a half gives us 5. Okay guys, so tractors, they are definitely heavy things, but if you look closely you'll see this one is a toy. That's not a real person in there. Ha, liars. But anyways, the total mass of the tractor and the driver is 1,660. Okay, so when we think about our equation of F equals ma, okay, ma, wee. Sorry, I'm writing with my mouse. It looks terrible, but never mind. If we're thinking about that, then we have mass, but we don't have acceleration. Now this is a distance time graph, and what they're asking us is calculate the speed of the tractor at the end of section A. That is a very nasty question, because when they say end, they are talking about that point in time. They're not talking about this whole thing, because that is the average speed. Okay, talking about that point in time right there. Now this section over here is acceleration. Can you see? Because it's got that curve there. If it was, the curve was in the other direction, we know that it would have been deceleration. Okay, so deceleration would go like that. But in this case it's acceleration. But they're not asking us for the average speed. They're asking us for the speed at the end of section A, which is nasty, as I said. But you know that when we look at this section B, it's a straight line. Is there any acceleration happening there? No, there's not. So if there's no acceleration happening in section B, it means that the speed is staying the same. And at the beginning of section B, the beginning of section B and the end of section A is the same place. And the speed will be the same here as it is here, as it is here, as it is there. So to calculate the speed of the tractor at the end of section A, you use the speed in section B, because at the end, right there in that moment of time, this is the speed that it maintained. Okay, and that's why I say it's really a nasty question. Most kids, when they did this, they just calculated the average speed over that first section, but unfortunately they specified end of section A. Okay, nasty. But then they told us also to calculate the net force acting on the tractor during section A. Okay, because the force is creating an acceleration. Okay, and to do acceleration, we know that acceleration equals the change in velocity over the change in time. And if we can figure out what the velocity is in that point there, we know that the beginning velocity was 0 and the end velocity is going to be the same as section B. I know it's a little bit counterintuitive, but just because this is the constant speed right there, because it's a straight line, we know that it's the same over the whole area. Over here we cannot tell exactly what the speed is in the different instances. We can give you an average, but we cannot give you the instantaneous speed, and that is what they're asking us. Okay, so first things first, we do acceleration because it's delta v over delta t. Now, can we calculate it? Do we have t? Yes, we do. Okay, so for acceleration, to get that acceleration there, we have to do change in velocity over change in time. And we have the change in time because for this force part of the question, we're going to look at this section. So t is going to be 30. Okay, and with t being 30, our change in velocity is the one that we need to get. So now, in a distance time graph, the rise over the run is distance over time. And we know that velocity equals distance over time. And more specifically, the change in distance over the change in time. Okay? So what we'll do is we'll take velocity of section B, because we're calculating that end of section A, that moment in time. So we're going to go from, our delta t is going to be from 30 to 90. So what do? We take the final time 90 and we subtract the beginning time 30. And that gives us, so 90 minus 30 is 60. So below the line is going to be 60. And I wish my machine wouldn't do that. It is really frustrating. But anyways, and above the line is going to be 120 is the initial distance. The final distance is 600. So 600 minus 120, 600 take away 120 is 480. Okay, 480 divided by 60 gives us 8. So now we have the velocity at that moment in time right there. Okay, so for acceleration, we know that change in velocity is it goes from 0 all the way up to 8. Okay, and let me just get a different color pen. So it goes from 0 all the way up to 8, and that's meters per second, isn't it? Alrighty, so when we look at acceleration, velocity over time, so it's going to be 8 divided by, and the time it took us to get there was 30. And that means 8 over 30 is 0.27 meters per second squared. Alrighty, and now we have to take this A, put it into that equation there. That means that F equals mass times acceleration, so 1660 times acceleration, which is 0.27, and I can't do that without a calculator, so let's look at the model answer. Okay, so it starts off by saying that the slope of section B equals the speed of the tractor at the end of section A. Okay, as I say, I think it's a nasty question, but hey, now we know. Okay, so when they ask you something, the speed at the end, you always use the next section's speed, especially, well, you make sure that the next section's speed is actually a constant speed, and then you use that. Okay, and so we said velocity is rise over run, velocity is change in distance over change in time. The change in distance is 600 minus 120 over 90 minus 30, and that gives us 8 meters per second. Then acceleration, we take that 8 meters, we put it into our change in velocity here, because it's the instantaneous velocity right there, divided by time, which is going to be 30 minus 0 is 30, and that gives us 0.27. And then F equals ma equals 1660 kilograms multiplied by 0.27, and that gives us 442.7 Newton. And if you did that, you got excellence. Okay, let's look at another. Newton's laws. Now this is the third law. When a force acts upon an object, an equal and opposite reaction force occurs. This is called the action-reaction force. Some people say for every action there's an equal but opposite reaction. So this person is pulling on this box and pulling and pulling and pulling and pulling, and eventually the box, the friction down at the bottom is overcome, because there's friction here. And the friction is overcome, and as that friction is overcome, the force of that friction, the negative force, is overcome, then it starts moving. Okay, but initially when they're in a dead standstill, your friction force and your action force is going to be equal. Okay, so the action force, the pulling force, is going to be equal until it gets overcome, and then friction, the drag is going to be greater, or not the drag, the pulling action is going to be greater. So for every action there's an opposite but equal reaction. Now just to remind you that the first law, Newton's first law, said that an object will remain in rest or in uniform or constant speed in a straight line unless acted upon by an external force. Something doing nothing will keep on doing nothing unless an unbalanced force acts on it. Something that's going at a constant speed will remain in a constant speed unless an unbalanced force acts upon it. Okay? The second law said, and this is F equals ma, when the forces are not balanced, the acceleration of an object, so A over here, the acceleration of an object is dependent on two variables, the net force and the mass. Okay, when something is accelerating, it says that the acceleration is dependent on the net force and the mass. F equals ma. Alrighty, so let's have a look at this one, mass and weight. We talked about mass and weight already, and we made it very clear that all objects have mass. Everything has mass. It is how massive something is. If there is no molecules, there is no mass. Okay, but mass is not the same as weight, because weight is a force. The weight force is how much gravity is pulling down on us. So mass refers to the amount of atoms or molecules or substance in an object. The formula for mass is m, and mass is measured in grams or in kilograms. Okay, so remember kilograms, kilo means 1000. So kilometer is 1000 meters. Kilograms is 1000 grams. Kiloliter is 1000 liters. Okay. The mass of an object remains the same regardless of its location. So if your mass is 60 kilograms, your mass is 60 kilograms. If I put you on the moon today, the moon has got 1/6 the gravity of Earth. That means on the moon, you will be the same size, but it will feel like you feel like your weight force pulling down on you is 10 kilograms. So imagine that. Everything suddenly will be multiplied by 6, how high you can jump and how big the stuff is you can pick up, because of the weight force, the amount of force that the planet or the moon that you're on is pulling you downwards. That is a weight force, and we should really try to talk about weight force, weight force, weight force. Mass is kilograms. Weight force is a force, and a force we measure in newtons. Okay? So weight is the downward force due to gravity. And it's the pulling of gravity. The weight of an object can change depending on the weight force can change depending on where it's located. Astronauts weigh less on the moon because of the gravity is less, but their mass is the same in both locations. The formula for weight is weight force. W force of the little w is weight force, and it's measured in newtons. Okay, so the reason why astronauts in space, their muscles deteriorate big time because they don't experience the same gravity, so their muscles are not working as hard. Okay, so here we have 3 blocks. They're all 2 kilograms of mass. So in other words, there's 2 kilograms worth of matter or molecules or atoms in there. Okay, but on Earth, the Earth is pulling it down at 20 Newton. And as it's pulling it down at 20 Newton, we know that that is 2 kilograms, 20 Newton. But on the moon, that 2 kilograms is multiplied by what is it? Yeah, so it's multiplied by 1.6, and that gives you 3.3. And over here, deep space, there is no gravity. That's why it is 0 Newton. So that is where we'll end for today. Can I ask you to please go to your side pads, open on page 39, and complete 39 all the way to 41. Remember, the more you practice, the easier this stuff gets. So please do the practice. Alright guys, I'll chat to you again soon. Thank you. Bye.